Okay, the next topic, which shouldn't take too long, hopefully, is to go through an overview of Java synchronization mechanisms. So we've talked before, why do we have synchronization? We have synchronization in order to be able to protect against race conditions by having mutual exclusion on critical sections and to coordinate interactions among concurrent programs. We're not going to show any code here. We're just going to talk about, well, we'll show a little bit of code, but we're not going to go through programs. So first thing, the very simplest form of Java's synchronization mechanism is the volatile keyword. And we kind of talked about it last time, but I want to give you a more systematic approach with cool graphics and stuff like that. So volatile is a keyword that ensures changes to variables are always consistent and visible to other threads atomically. So it's kind of like the transporter technology on the Enterprise. You either beam yourself to your destination or you don't go anywhere. You don't beam like half a person, right? That would be bad. So it happens all at once. You can't stop. When something's atomic, you can't stop in the middle. It either works completely or it doesn't happen at all. And there are no side effects visible until the entire thing is done. So that's what it means to be atomic. Now, you'll see that that's not the only way to get atomicity is through using volatile. In purely sequential programs, things where stuff goes one at a time in a single thread, there's no need for volatile. And that's because if the one thread of control writes something to memory and then the same thread of control subsequently reads from memory, it reads and writes to the very same thing. Or it reads and writes to a register that it has total control over. So that's a consistent, strongly ordered memory model. Reads and writes of most Java primitive variables are atomic. The only exceptions are long and double, which are 64-bit instead of 32-bit, and they therefore will straddle machine boundaries in the Java virtual machine, which assumes 32-bit instructions. And you can take a look here for more information about that. In concurrent programs, however, volatile is needed. And so if you take a look, you can read about volatile in general. You'll see in a second that volatile in Java behaves quite differently from volatile in other programming languages. The reason why we need this is because in the Java memory model, one thread may not see the latest value of available changed by another thread due to caching in registers, in instruction caches, data caches, and so on. So here we have a program, and currently you have 3 threads with different values and 3 caches. This thread sets the non-volatile value to 11, and this thread shortly thereafter reads the value of U, but this was never propagated up to main memory, so this guy reads the old value out of the cache. And this can be quite a problem if there's some reason why thread 1 and thread 2 need to coordinate with each other. So Java defines the volatile keyword to address this kind of a problem. You can read more about it here. There's also lots of other stuff you can read about volatile online. When you write to a volatile variable, it never stays in the cache. It's always flushed to memory. And in fact, the whole cache line is flushed. So typically other things are flushed as well. But at the very least, the value you just wrote is going to be flushed to memory. So if this guy sets V to 11, then when this guy reads V afterwards, he will get the value of 11. Yes, Colin?
For having to read and write directly to memory every time, are there big performance implications to this?
There's a hit, right? It's going to take longer. But would you rather be fast and wrong or a little slower and right? That's the trade-off. Moreover, if you use volatile, reads and writes of all primitive variables are atomic, not just for longs, not just for ints and shorts and characters and so on, but longs and doubles are also going to be atomic. There are some limitations with volatile, however. It's very simple, and it's meant to assure atomic reads and writes only. Here's a very simple example with the singleton pattern. You might remember the singleton pattern if you took 251. And in the singleton pattern, you have this issue about what happens if multiple threads call into a singleton before it's been initialized the first time. And there's this thing called the double-check locking optimization pattern. And the way you implement it in Java is you use volatile to have an instruction, or an inst, singleton inst. And then the idea here is that you only synchronize when inst is null, so you lock here. And after you've initialized this thing, after you've set inst to something, then this check will always be false, and so you won't reinitialize yourself. However, using Volatile, it works fine for this, but it only works for reads and writes. So you can see here we're writing we're reading a volatile variable, and we're writing to a volatile variable. Those are atomic operations. But things that span multiple steps are not candidates for being synchronized with Volatile. This is an example we talked about on the whiteboard last time. So here's an example where we've got a counter, and we're going to increment an integer. We have thread 1, which increments this. We have thread 2 that increments this. But this call involves 3 steps: loading the counter into a register, incrementing the register, storing the register back into the counter. And depending on the order in which these things happen, if these are interleaved and suspended, you end up with stuff being inconsistent. You have race conditions, which is obviously undesirable. So the point there is that you're going to need more powerful mechanisms if you want to be able to synchronize that stuff. Likewise, if you define an array or an object as volatile, only the reference is volatile, not the actual contents that you're pointing to. So here's an example where vector is volatile, but the internals of it, the array of objects and the element count, these things are not volatile. So if you need to synchronize, you're going to have to use a more powerful mechanism. And in fact, that's exactly what vector does, which is one reason why you probably want to use it for your specific notification pattern for the simple semaphore for its fair model. So here we would use synchronize, which means that everything in here will be atomic in that block of code. Little side note, I won't hold you accountable for this, but it's worth knowing. The semantics of volatile in Java are not the same as in C and C++. In C or C++, in C and C++, volatile does not mean that the operations are atomic or that there's a happens before relationship with respect to storing and receiving things. They don't give you atomicity. Instead, what volatile means in C++ and C are that the compiler should not do aggressive optimizations and eliminate code that appears not to actually be needed. So if you take a look and you read this article here, it'll explain to you the semantics of C and C++, and it says very, very specifically that the usage of volatile keywords as a portable synchronization mechanism is discouraged by everybody who knows what they're talking about. So you don't want to use volatile for that. All right, next topic. We'll go through this quickly because we're going to go through it in more detail later. So volatile is the very, very simplest form. The next type of thing, next level up, are monitor objects. And these are built into Java. There are 2 things they support. They support mutual exclusion, so only one thing gets into the critical section at a time. And they also support coordination, which means that things can move back and forth and other interesting things happen, and you can park yourself by waiting and notifying and so on. Any Java object can be used as a monitor object. So we could trivially solve our simple blocking queue problem we had before by making things synchronized, which gives you mutual exclusion. And you can even have blocks of code that are synchronized. But keep in mind, synchronization alone is not sufficient. We also need to be able to allow things to wait on stuff. So as a result, monitor objects also provide support for waiting. So you can have what's called an entrance queue, which guards the entrance into the critical section. This is used for mutual exclusion. And then wait queues are used for coordination. That's basically what monitor objects give you. And we'll talk a lot more about monitor objects. The last set of things, which we're not going to talk about a lot right now, we'll come back to them probably later in the course, are other synchronization classes. These are part of the Java libraries. They're in Java util concurrent and Java util concurrent lock, which you can read about here. And there are a whole bunch of these classes. We're going to talk about just a few of them. Reentrant lock, which is basically a mutex or mutual exclusion mechanism that gives you more than you get with the built-in monitor lock mechanisms in terms of synchronizing with an entrance queue. There's some extra things they do. A reentrant read-write lock, which you're using for assignment 2A if you're a grad student, which allows you to be able to differentiate between readers and writers to speed things up for readers if you have multiple readers. Semaphores, which you're implementing right now, which are these non-negative integers that allow multiple threads to get access to a limited number of resources. condition objects, which are used to block until certain conditions become true. That's kind of the way that the wait and notify mechanisms work in a monitor object. They use something akin to a condition object, although the condition objects used with the monitor object implementation are implemented at a lower level using C than the condition objects that are implemented in the libraries, which are largely done with Java code. And we'll talk more about those details later. And then we have things called countdown latches and cyclic barriers, which are typically used for groups of threads to coordinate their execution, to be able to provide points where they all wait for something, where they all wait for each other to get to that certain point, and then they continue on. The example I'll show when we get to that part of the class is like when a bunch of horses start out a race, they all kind of walk up and get in those stalls where they start the horse race, and it's not until all the horses are in position that they can all start to run. So we'll talk about some examples like that. Those classes that we just talked about briefly, we outlined, are all distinct from the built-in monitor object mechanisms. And the synchronized keyword, wait, notify, notify all. You can see here for more about that. The built-in monitor objects are more fundamental and pervasive, so we're going to cover those things first. Okay, so that well, let me just do this. We've got just a couple seconds. I want to get this out of the way. So as you'll see, synchronization is very important, and we use it for a bunch of reasons we talked about before. Here's the key take-home point from these slides. We're going to spend way, way more time when all is said and done on synchronization mechanisms than we do on Java threading. We're going to spend we pretty much covered Java threads in a short amount of time. We're going to spend a lot more time on all these synchronization mechanisms and some of the scheduling mechanisms they provide. And the reason for that is that complexity in large systems, be they computer systems or social systems, is usually more a function of coordinating stuff than it is in things just doing their own thing independently. Independent operations are easy. Coordination is hard. Anybody recognize this? So when I was in India, I also saw a lot of this too. It's amazing how well coordinated. It really is amazing. We would be in taxis, and I was like convinced we were going to die. And the taxi driver would just like nimbly move through the crowds, and very few accidents. Everybody they get this close. It's like they have ESP or something, and they know when they're getting too close, and they stop. It's just amazing. People's situational awareness there is out of this world as far as their driving surroundings. The other rule, by the way, is biggest vehicle wins right of way, right? So it doesn't matter what the rules are. Whoever has a bigger vehicle, they get the right of way. We're going to cover all these things later, and I'll talk about how they're implemented and show lots of examples and how Android works. So what we're going to do today is we're going to talk about commonality and variability in Java synchronizers. So if you recall that the Java synchronizers basically deal with things like reentrant, read-write lock, reentrant lock, semaphore, condition object, all that kind of stuff. And there's a lot of things that are in common there. So here's one thing that's in common. If you take a look at the documentation for the Java util concurrent locks package, you'll see that there's a set of interfaces for condition, lock, and read-write lock. And those are just good old interfaces. If you take a look at the code, which we'll look at in a second, you'll see how they work. And these interfaces can be implemented lots of different ways. Out of the box, they're implemented by reentrant lock, which implements lock, and reentrant read-write lock, which implements read-write lock interface, and condition object, which implements the condition interface. But you could write your own. You're not limited to those. You could write a non-reentrant lock that would implement the lock interface. And you'll see in a second why they have this interface. It simplifies lots of things, and it means you can have the interface for your locking abstractions very much decoupled from the implementations of how they work. Lawrence?
I'm trying to remember, can you inherit one interface from another?
Can you inherit an interface?
Or like extend an interface with your own interface?
I think you can, yeah. Yes.
Is there ever a situation where you'd extend one of these Java interfaces to provide additional functionality?
Oh, absolutely. You're going to see gazillions of cases where that happens. Yes, yes, yes. Yeah. And in fact, almost everything ends up doing that. You'll see in just a second. Here's the source code. We're going to look at all the source code here in just a minute, so I won't go there, but that's where you would go look if you're doing the Java version. I'm sorry, the Android version. There's also, of course, Java code. Java code implementation is very similar to what's in Android. Now, so that's the common interface that many, not all, but many of the synchronizers implement. Then there's also a common framework that most of the synchronizers use to carry out their behavior. And it's called AbstractQueuedSynchronzer. And it's kind of at the heart of almost all the locking mechanisms that rely on some kind of blocking queues. And, by the way, the implementation under the hood uses the specific notification pattern we've been talking about, except it just does it in a much more deep way than we've done. And you'll see what I mean about that in a second. So AbstractQueuedSynchronizers is kind of at the heart of everything. So reentrant lock, semaphore, countdown latch, future task, reentrant read-write lock, thread pool. These are all things you get out of the box with standard Java that are related to AbstractQueuedSynchronzer in one way or another. And we're going to look through some of the source code of AbstractQueuedSynchronzer here in just a second. And that's where the source code is, so we'll look at that. OK, now, if you were to poke around in AbstractQueuedSynchronzer, as we will do, you would find some interesting things. What it does is it's used to synchronize on stuff where the state of the synchronizer can be represented in a single integer. And so here's what it looks like. It's a private volatile called state. So it's just a volatile int. That's the main piece of data that this thing provides. There's other stuff it has too, but that's the main data that it uses. And it's got a pair of setter and getter methods to set and get that state. And you'll see those used all over the place in the code. OK, so that's how it represents things. Anything that can be represented as an integer that needs to be managed atomically can be inherited from AbstractQueuedSynchronzer. It also defines a method called compare and set state. And we're going to talk a bit more about that in a little bit. We're going to talk about set and get operations and so on. And these are typically implemented down in hardware. And in fact, compare and set state is actually implemented by something called the unsafe class. There's actually a class in Java called the unsafe class. And if you go to this link, you can find out all about the unsafe class. It's basically got all the things in Java that you're not allowed to do in Java, right? It's kind of like people in North Korea probably watch a lot of TV and movies that they don't let anybody else watch, right? The people who run North Korea, they can do that. They have special privileges, right? Everybody else is starving on a commune, and they're like watching NBA highlights of the Chicago Bulls because Dennis Rodman's like BFFs with Kim Jong-un. So there's this thing called the unsafe class, and we'll look at that a little bit later in more detail. Another thing that's provided is both exclusive and shared mode. So exclusive mode means just one thing at a time. So like a reentrant lock provides exclusive mode. But some synchronizers, like read-write lock, that gives shared mode. So multiple things can be sharing access at the same time. So semaphore and countdown latch also use shared mode. Reentrant read-write lock uses shared mode, of course. And we'll see how that works. Now, does anybody remember what the defining characteristics of a framework are? What's the key thing of a framework? So a framework is an integrated set of components that collaborate to provide a reusable architecture for a family of related applications. And they're characterized by three things: so-called inversion of control, domain-specific structures and functionality, and they're a semi-complete application. What all that means is they define these things called hook methods, kind of like the template method pattern. And the framework is written in terms of calls to hook methods. And of course, the framework implementer doesn't know how to implement the hook methods, but it knows that the subclasser of framework abstract classes does know. And so you're going to see that the AbstractQueuedSynchronzer works exactly that way. It provides all kinds of things that do all the heavy lifting of all these locking mechanisms with block queues and specific notification and so on and so forth. But it assumes that you, i.e. whoever's coming along to customize AbstractQueuedSynchronzer, know how to acquire and release locks without blocking. So that's all it expects. You have to know how to do those kind of things. There's actually a couple other things it expects too, but those are the main things. So if you actually look at the implementation, which we'll do, you'll see that they define these things basically as methods that just throw the unsupported operation exception. So you have to fill them in. Okay, so another interesting thing is that many of the synchronizers that are part of Java use our good friend, the bridge pattern. And they do this to be able to do just what we did when I showed you my solution for the specific notification semaphore implementation. They do it to decouple fair and non-fair semantics. So for example, and we'll see which ones they are in a second. If you recall, the intent of the bridge pattern is to decouple the abstraction from the interface, or the abstraction, which is the interface, from the implementation so the two can vary independently. In our particular case, we're just varying the implementation. You can see the description here. The particular variants of this common model that do this are reentrant lock, reentrant read-write lock, and semaphore. Those are things that use this particular technique. And what they do, if you look at all those implementers, imagine replace the capitalized word synchronizer with semaphore, or reentrant lock, or reentrant read-write lock, or whatever, right? What they do is they all look exactly the same. They define a class called sync, which is a nested class, which is an AbstractQueuedSynchronizer. So it inherits from AbstractQueuedSynchronizer. And then they define an instance of sync as a method in the class, or as a data member in the class. AbstractQueuedSynchronizer is the guy that has all this implementation stuff defined. Then down here in the constructor, what they do is, depending on whether you say you want things to be fair or not, they either allocate a new fair synchronizer or a new non-fair synchronizer. And of course, fair and non-fair synchronizers inherit from the sync class, right? So sync so fair sync and non-fair sync inherit from sync. And you can see by default, they all start out to be non-fair, because non-fair is more optimized. All right, so you're going to see that this is a pattern that gets used over and over again. And then the actual implementation methods in the class are simply going to forward to the appropriate implementation. And it's dispatched, of course, using the magic of dynamic binding, right? So you, as an application developer, call lock on a reentrant lock, or you call acquire on a semaphore or whatnot. And under the hood, that turns around and it forwards to whatever implementation was selected in the constructor. So that's just good old-fashioned classic bridge pattern, right? Here's the abstraction. Here's the implementation. This thing can be set by the constructor based on a flag you pass in. Any questions about that? So if you go look at the Gang of Four book, or you go back and review the notes from 251 or the videos, you'll see exactly this model. The methods for the implementations of fair sync or non-fair sync, in turn, call down to the appropriate methods defined in AbstractQueuedSynchronizer. So they're able to reuse the vast amount of its implementation. You'll see later this is just the template method pattern. In fact, here it is. Here's the template method pattern. If you recall the template method pattern from the Gang of Four book, template method said we have an abstract class with some methods, and we have these things called a template method, which is written in terms of some code and some calls to so-called primitive operations, which we call hook methods. And then a concrete class comes along and fills in some of the concrete methods. So the pattern defines the skeleton of an algorithm in the base class, and then it lets subclasses override these things. Here's an example. Here is the acquire method, which we'll look at in more detail in AbstractQueuedSynchronizer. The acquire method in AbstractQueuedSynchronizer is a template method, and when it's called, it calls to the try acquire method, which a subclass of AbstractQueuedSynchronizer must fill in, and it tries to acquire a lock. And if it doesn't get it, then some other stuff happens, which we'll talk about later. But that's a good example of the template method pattern. So you're filling out a lot of the details, and you're leaving hooks where subclasses come along and override these things. So why am I showing you all this stuff? Well, first of all, it's a great way to connect together all the patterns we learned in 251, which had nothing to do with concurrency, and had nothing to do with Java, and had nothing to do with Android. And now we're connecting it in a context where we have Java, Android, and concurrency. But the patterns are still applying. So that's kind of cool. So it helps bring things together. And it's also illustrating how even relatively low-level code, right? I mean, this is the bowels, almost the very, very lowest floor implementation of the concurrency mechanisms themselves are using patterns. So it's kind of a good example that patterns are useful in almost any circumstance. Another thing that you see a lot in concurrency code is this idiom. You'll often see there being a lock, which is a data member of the class. And then when you come into a method, the first thing it does is it grabs that lock and it sticks it in a local final variable. Now, I have a feeling this probably was an optimization for an earlier version of Java's compiler. And if you read this article, it explains some of the thoughts behind it. But the idea was at some point, doing this made the code smaller, generated smaller byte code. So I don't know whether that's really still true anymore, but you see that a lot through the Java code. And then, of course, you also see this idiom all the time. You acquire the lock, and then you do your thing in a critical section, and then unlock takes place in the final, or the finally portion of the block. And as we talked about before, this is sort of in lieu of Java having destructors. And we'll talk more about that idiom a little bit later. OK. What I want to do now is I want to take a look at some of the AbstractQueuedSynchronzer source code. So here's the source code. We'll look at it in a second. This is actually a stripped down interface of this thing. There's actually like another dozen or so private methods. These are just the protected and public methods in this class. This class is a gigantic class. And some of the methods, like these are all protected methods. These are the ones that you have to override, like try acquire, try release, and so on. And then we have a bunch of other methods that are public, that are used by implementations of stuff to do their work. And then there's a bunch more private methods that do even more crazy things. So there's all kinds of stuff that's going on there that's quite interesting. So here's AbstractQueuedSynchronzer. And as you can see, it extends AbstractOwnableSynchronzer. And it implements Java I/O serializable. So here's AbstractOwnableSynchronzer. And this class basically just keeps a thread ID, current or exclusive owner thread. This is the thread that currently holds the lock. And it has setter and getter methods for it. Trivia question for those who are familiar with Java. What does the transient keyword mean? Robbie?
It means when you serialize it, just ignore it.
When it's serialized, it gets ignored. And why would you typically serialize something? What would you ever why would you serialize something? You're going to pass it between different processes or store it in a file. And the point there is there's no sense storing an thread ID because it's going to be different every time. So it doesn't mean anything. There's no sense in trying to store it in a persistent way. OK, so that means that we have a couple methods to set and get the thread owner of this thing. There is also a gigantic class called the node class. And it has lots of things in it. I'm not going to go through all those things. This is basically, remember when we did the specific notification implementation from last time, and we had a thing we called the wait node, and the wait node kept track of some state, and we basically used that to kind of wait on. Well, that's what this node is. This node is what's going to be used to help wait, except the waiting is done in quite a different way than our other stuff was for specific notification. By the way, if you look for the word specific, there it is. Each node of the queue serves as a specific notification style monitor holding a single waiting thread. So there you go. That pattern that we talked about appears in this implementation. All right. So there's node. Here's state. This is the state we were talking about. And here's get state and set state. These are just all part of that class. Not much exciting there. Here's the interesting method, compare and set state. We're going to talk a little bit later about two different ways of getting synchronization at the low level in a system. And it works by something that's called either compare and swap or test and set. I'll briefly talk about compare and swap here, and then we'll cover it later when we get to Rantrant Lock. Compare and swap basically do the following, as you can see here. You give it the value you expect, and if the current value of the lock equals what you expect, it atomically sets it to update. And the way that typically works is what you do is you say compare and set state, and you give it a 0, which means is the lock unlocked? If it is, lock it. And those things are done atomically. And this is typically done in a spin lock or polling-like manner. We'll see a little bit more how it's used later. Under the hood, this just calls down to the unsafe compare and swap int method, which does some other cool stuff, which we're not going to show that code. It's probably written in assembly code for that matter. Self-interrupt is kind of a fun method. Self-interrupt basically is used for a thread to interrupt itself under various circumstances. You'll see how that gets used later. Here's the acquire method in AbstractQueuedSynchronzer. This gets used by lots of other synchronizers like reentrant lock and so on. And what it does is it comes in and it tries to acquire. This call, this try acquire call, is a template method, hook method. Right? This is a template method, acquire. Try acquires the hook method. And that's what you have to write. We'll look at an example in a minute. So if you acquire, then we're done. So if you come in there and remember, try acquire, the semantics of try acquire are that you check to see if there's no waiters, and if there's no waiters, you become the owner. So that's what try acquire does. It also works recursively. We'll see in a second too. So if you were able to acquire the lock and there was nobody who owned it, you get it right away. There's no blocking. That's what's sometimes called a lock-free implementation because it doesn't lock in that case. If there is contention, however, if somebody already owns the lock, we don't want to sit there and just spin. So what we do then is we call another method called AcquireQueued, and we'll come back and look at AcquireQueued in a second. AcquireQueued is going to basically do the specific notification pattern technique of parking your thread on a wait queue for somebody to release the lock. Okay, and then once everything happens, you interrupt yourself, which is used by other things up the chain. Okay, so we'll come back and look at that. So that was one thing. That's what acquire does. Here's acquire interruptibly. As you can see, all it does is it comes in there and it checks to see if it's been interrupted. And if it's so, it throws the interrupted exception. Otherwise, it does do acquire interruptibly, which we'll look at in a second as well. And then there's also a timed acquire. And then a final thing here is release. So release, of course, is going to let things go. So you come in here. It's a template method also. We try to release, which calls up to the code that we write, which does a non-blocking release. And if we are able to successfully release, then we go ahead and we unpark our successor. We'll talk more about parking and unparking in a second. Parking is much like waiting. Unparking is like notifying. So that's release. All right, so those are those guys. And then we have some of the implementation methods. Let's go take a look at a couple of them. Here's AcquireQueued. If you recall, acquire. Here was acquire. So acquire would call AcquireQueued if it couldn't actually get the lock. And I'm not going to go through this code in great detail. It's very, very interesting, but it's more effort than we want to go into. We come in here. This is the guy that's going to basically go to sleep until he gets a chance to be released. So he comes in, and the first thing he does is he checks to see from the point when he was called earlier whether or not he is now able to run. And he's able to run if the node that we would be waiting on is the head of the queue, and we can acquire it. So if that's the case, we're done. If that's not the case, in other words, if we're not at the head of the queue, or we can't acquire that because we got people who are ahead of us, we come down here and we call several things, and we end up calling park and check interrupt. So let's go take a look at park and check interrupt. There we go, park and check interrupt. So park and check interrupt calls to something called lock support park. And lock support park, I'm not going to show you the code, but basically what it does is it puts itself to sleep, waiting for someone to unpark it. Who's going to unpark it? Well, of course, the guy who does the release calls unpark successor. And unpark successor does a bunch of stuff. And if everything goes according to plan, he unparks the thread. So that will wake up somebody who's waiting, and he'll have a chance to go. So those are some of the low-level methods that are used inside of the AbstractQueuedSynchronzer. Now again, we could spend probably a month just going through all the code. It's very, very, very subtle and detailed, and uses all kinds of clever techniques that maximize caches and tries to make everything as efficient as possible without spinning too much, without blocking too much, and so on. But that's basically AbstractQueuedSynchronizer. The good news is you don't have to know how it works. You just have to know how to use it. And if you take a look at the documentation for this class, it actually gives you a nice example that shows you, for example, how to implement a very simple non-reentrant lock that uses the mechanisms here. You can see what you do here is you say, I've got a class that's a mutex which implements lock. So there's an example of having a class that implements a lock. And then we could come down here and we could have a sync class which extends AbstractQueuedSynchronizer. Then we would go ahead and fill in the try-acquire method and the try-release method. Remember, these are the hook methods you have to fill in if you implement AbstractQueuedSynchronizer. And you can see here that try-acquire will call down to this compare and set state method, which is the one that does the unsafe check. It does basically the check in hardware to see if we have exclusive access. So what it's saying here is, if the lock is unlocked, lock it and return true. And if that works, then we become the exclusive owner. And with try-release, then we go ahead and say, hey, if it's not locked already, then throw out an exception. Otherwise, go ahead and release the lock. We'll talk about some of that stuff a little bit later in other ways. OK, any questions about AbstractQueuedSynchronizer?